Hi, Physics 30s. We're going to go over this year-end practice test number 1 here. Hopefully it doesn't take too long. All right, so we got here the risk of motorists being injured in a collision is reduced when an airbag seatbelt is used compared to the identical collision with no airbag and seatbelt. The change in momentum, which is the impulse, will remain the same because you have to kind of imagine, like if you're driving along 50 kilometers per hour and you come to a stop, your change in speed is going to be 50 kilometers per hour. The mass of the car hasn't changed. So in both situations, mass times change in velocity, it's just going to be the same. So that's going to stay the same. And the stopping force will be decreased because the seatbelt is increasing the time. All right? So that's obviously it's going to be A there. So here we go. So at the instantaneous velocity, instantaneous speed of the car at 1 second here, right there is going to be something. So we got this force time graph over here. Every time we have a force time graph, I know we're going to do the area of this force time graph here. So what do we have here? The initial speed of the remote car is 3 meters per second. It experiences the force in the direction of its motion. So it's going to speed up, which makes sense. So probably cross off A and B. I don't know why it would slow down. If the force is in the same direction, it's going to speed up. What is that instantaneous velocity at that 1 second mark? So I don't know why they don't go all the way up to the... Two students analyze the motion. One looks at the first 1 second, and then another one looks at the 1.5 interval. So I don't know why. Maybe there's more questions here. 1 and 2. Okay, so there's going to be another question. Oh yeah, there's the, so it's asking for the impulse of that part. So to get the instantaneous speed here at 1 second, I'm going to have to find the impulse of this graph. So what I'm going to do here, I'm just going to snip this out like I've done previously. Making sure, look at my units there. So we got a force, we got time. The units are not really weird here, so that's good. So we just have to remember that when we do these, the area that's under this graph here, and I want to go up to the 1 second mark for the first question. That area, that is my impulse. Okay? So to calculate my, it's going to be length times width, right? But remember, that's just going to be force times time. That's my 2 units here. So force times time is my change in my momentum, right? And we know a few things. So I can calculate my final. Actually, I calculate my initial here. So I'm going to go force times time. So force, I'm typing at this weird kind of angle here. That's fine. So I got 8 newtons times 1 second. Okay, that's just 8. I don't even want to bother with my calculator here. So on this side, we get 8 newton seconds. Over here, to get my initial momentum, I'm going to go mass times velocity. So I have to go back to my question. I just got to figure out what the mass and the velocity of this car is here. So it's a 5 kilogram car, velocity is 3 meters per second. Okay. So we got mass times velocity. What did I say? It was 5 times 3, so it's 15. So 15 kilogram meters per second. Over here we got 8 newton seconds. I know there's a mix of units, but I'd like to have impulse as newton seconds. I'd like to have momentum as kilogram meter per second, but they are essentially the same unit. I'm going to add on that 8 there. So I'm just going to move that over to that side. And I get my final momentum to be 23 kilogram meters per second. And remember, that's equal to mass times velocity. And I'm getting right down to the bottom here. So what I'm going to do, I'm going to divide my mass over. That's just 5 again, so I'm going to divide by 5. And we get 4.6. Let's go back here, 4.6. Awesome. Now all they want here is the impulse for the second part from 0 to 5. So I want to do the whole impulse. I already have, if I go back here, I already have 23. So I can cross off A and B, probably C as well, unless this ends up being much smaller than it is. But we're looking for the impulse from 0 to 1.5. Remember, impulse is change in momentum. Oh, sorry, the impulse for that first part is 8. My bad. So 8 is for that first part. Okay, so it could be any of these answers. That's fine. So this first part, 8 Newton seconds. I just need to determine what the second part is and add that on. So this area is going to be 1/2 base times height. It's a triangle. So 1/2, my base being 1/2 a second, my height being 8. So 1/2 at 1/2 of 1/2, or 1/2 at 1/2 of 8 is 2. Okay, so it was going to be A. Sorry about that. So that's going to be 2 newtons. That's going to be 8 newtons per Newton seconds there. So the answer is going to be A again. There you go. In the diagram of the region Y represented... Oh, am I missing something here? Seems like I'm missing something for this test. This might be the... Use the following information for questions 4 through 9. So that's the one right there. So I had to kind of we have to scroll back. Okay, so we have a problem here. So this is question 4 in diagram 2. So diagram 2 is this one here. So I have to skip back and forth here a bunch of times. But it says here, let's go back here. In diagram 2, the direction of the electric field in region Y is represented, and it gives you some directions there. And then, okay, let's do that. So let's diagram 2 first. So in diagram 2, I want to know what the electric field. Okay, so we got an anode and a little spike there, the central spike. So they're saying that the anode here is positively charged. You got this magnetic field that's in there, but they want to know which way the electric field is. So remember that when it comes to a positive charge, the electric field comes out because that's the direction that... Yeah, so that's the direction in which the... Oh, the spike is for that. So that's the direction a positive charge would go. So if the positive is on this side, the electric field is going to be going to the right. So if I were to snip and do that, I'll show you what it looks like. So in diagram 2 here, so if I were to draw my electric field because of this positive particle or positive anode here, my electric field is going to go that direction, all right, out from the positive. All right, so let's go to that question. So A, got a lot of A's so far. Okay, as xenon ions move through region Y, as labeled in diagram 2, so this diagram 2, it's these positive ions. So I'm looking at this picture here. Okay, so positive ions moving through there. They experience both electric and magnetic force. The direction of the magnetic force they will experience as well. So because they're positive ions, when they move here, this is also going to be the direction of those positive ions because they're repelled by the positive piece. So they're going to be moving that direction. So then we pull out our hand rule, all right? Let me see if I cover my face up. Okay, so we're going to pull out my right hand, actually, because we have a positive charged particle. I'm going to put my thumb in the direction of the particle, and it depends on where we are, all right? It says in region Y. Region Y is the bottom part of this. Yeah, it's right here. Region Y is that bottom part. So my fingers are going to go up. So it looks like, because I'm using my right hand, it's going to be out of the page, right? Yep, so out of that page there. So you can see how my hand is oriented here. So my thumb is the direction of the particle. My finger's in the direction of the magnetic field. My palm is in the direction of the force that's being pushed out there. So we got out of the page. So that represents by a dot. There you go. It's region Y, so I'm assuming that's the one that's below. Yeah, so if it's above, it'd be the other way around. So they're going to create this kind of circular path here. All right, those xenon particles enter the thrust chamber at a negligible speed, so small enough that it could be considered 0. The minimum distance between the anode and the virtual anode required to produce the exit speed. Okay, so I got to read a little bit more into this. So we have like an initial velocity of near 0. That's what negligible means. And they want to be leaving the system right here at this 15,000 meters per second. All right, so we got this voltage here, electric field intensity where the xenon enters. You got the magnetic field. That's probably this area here. So what do we want to try to find again? What's the minimum distance between the anode and produces the electric field? Okay. Oh, to produce that exit velocity. Okay. So our goal here is to find possibly the voltage. So if I can find the voltage right here, I have the electric field already. I can rearrange this for D and get the answer for that. But to get the voltage, I'm going to be using the delta V formula, the other one. Right? So the other one, I'm just going to give myself some space here to do some work here. Okay. The other formula says that, I got to turn my head around, delta V is equal to delta E over Q. All right? Nope. Not let me write on this thing for now, just one second. There we go. Delta V is equal to delta E over Q. So I'm going to find my delta V this way by finding my change in my energy. So my change in energy, which is final minus initial over the charge. Now the charge here is denoted by this little symbol, this plus here. That just represents that this is plus 1e, which is 1.6 times 10 to the negative 19 coulombs. Right? If it was a 2 plus ion, then it'd be 2 times that. Okay, so now we know the charge. We can find the voltage by going final minus initial. They say that it's negligible. So this initial energy, because we talk about kinetic here, right? Because remember, if this is conservation energy, I'm going to lose potential. I'm going to gain kinetic. They're going to be the same amounts. So you can either talk about either one. Most of the time we talk about kinetic here. So to find out what that final is, I'm going to have to go 1/2 mv final squared divided by the Q, and that's going to find the voltage. Okay. So I'm going to go 1/2 times the mass of xenon. I don't know if they give that to us, do they? Oh, they do right there. All right. So 1.2, 2.9, negative 25. And I'm going to times it by the exit velocity squared. Make sure I put that in properly. So we get, oh, and then we're going to divide it by the charge. Oh no, just one second. Oh. Okay, so I got a voltage of 153.9-ish. Okay, so got a bunch of decimals there. So now we have our voltage. So what I'm going to do is I'm going to take that voltage and I'm going to use the other formula that's behind my head here. All right, E is equal to delta V over D. I'm going to solve for D. So I'm going to times the D up, divide the E down, and there we go. We got 153 point and I'm going to divide that by that electrical field there, 10,000, 1.0 times 10 to the 4 volts per meter. Cool. All right, let's do that. So we have about 1.5 centimeters or so. I don't know what they want for an answer here. Just one second. I have to go back here. Is it numerical response? No, it's just not numerical response. You just want the answer. 1.5 times 10 to the negative 2. So that's going to be a C. There you go. Now, keep on going. So while in the thrust chamber, the xenon experiences an impulse. No. While in that thrust chamber, impulse. Remember, impulse is going to be change in, let me just go back here. So impulse, there's two things. It's force times time, or it's mass times change in velocity. So that's going to be final minus initial. Initial is close to 0. So this is just going to be mass times my final velocity. So this seems like a pretty easy question. 2.1 times 10 to the negative 25 times my final velocity, 15,000 or so. Okay, so we get an answer of 3. Oh, I should probably write this down. I want scientific notation. 3.285 times 10 to the negative 21. So what do they want? So they want 2 sig digs and then the 2 negatives. So that's very key. They're telling us a hint here. So this is going to be a negative exponent, which is true, which we have. Okay, negative 21, and they want the 2 sig dig. So we're going to have to round. So it's going to be 3, 3, 2, 1. 3, 3, 2, 1. Because you got to round that up. So that 2 point, or the 3.2 becomes a 3.3. All right, keep on going here. Xenon. Xenon, let me move this out. Reaches the cathode at a speed of V1. When the xenon collides with the stationary electron in the virtual cathode, the xenon form. What's the relationship? Oh, so it's going to be a collision here. Xenon atom. Where they collides with the stationary, and the xenon atom formed has this speed. So they come together as one thing. Okay, so it's kind of a weird little question. So they form together to produce this atom. So we've got this ion comes along and produces an ion or an atom. So it's just a nice little collision question here. So let's just set up the equation. So we've got this conservation of momentum. So I have to use gray here. So the momentum before, if you remember this correctly, is equal to the momentum after. Okay, so before the electron is stationary, so all the momentum is just in the ion that we have. All right. Afterwards, it's all together. Well, I guess I could put here plus the momentum of the electron. All right. And then this is equal to the momentum afterwards of the atom. They're combined together, so they have this new mass of the atom. Now, because the electron is stationary, it's at rest here, we call it 0. It's really just going to be the mass of the ion times its velocity, 1, because it comes in with that speed. And then it's going to, afterwards, it's going to become the mass of the atom with the velocity 2. So I just divide the mass of the atom over to the other side, and that's my velocity 2. So that would be ion over atom. So we see here. Yeah, there you go. Now these other ones here, they're like ion, electron. That's if you forgot the mass of the electron before times 0 is 0, then you might have just left that there. Oh, a new question. Additional information. Okay. The length of time in hours, the type of propulsion must exert in order to increase the speed by 12 meters per second. So they're giving us a change. Okay, so remember that impulse can be calculated 2 ways here. All right, so I got this information on this side here. That's going to be helpful. So let me just snip this over here. I want the time in hours, right? Yeah, 12 meters per second. I'm just going to snip this here so I can do some work on it. Okay, so remember, impulse is calculated either 2 ways. We got mass times change in velocity is equal to force times time. And that's what we're looking for. We're looking for that time. So time is going to be mass times change in velocity over the force. So we got the average force right here, so that's nice, right? We have this exit speed I'm not too concerned about. We're just trying to get this satellite up to a certain speed. So we know the change in speed. We know the force. We just put all this stuff together here. So we got mass, 2,500 kilograms. Okay. We got a change in velocity that needs. It's got to get up to 12 meters, or change by 12. And we have this number here, this force. So put it all together, 2,500 times 12 divided by 0.02. So we get 1,500,000, and because these units here are all going to be in seconds, all right, so we get 1,500,000 seconds. And they want this in hours. So to get it to hours, what I'm going to do is I'm going to divide by 60 to get to minutes. So that's 25,000 minutes. And divide by 60 again. And you get 417 hours if we go with that. I don't know what they want for an answer. Is it just, yeah. Oh, did I mess up somewhere? Let me just double check my answer. Times 12 divided by the average force divided by 3,600. You get 416 hours. So they put this here. That's the number in seconds. Am I missing something here? Let me just double check something. Okay, unless you guys can figure out a reason for it, I think the answer is supposed to be B. I can just double check that here. So we submit this and you can see here, oh yeah, that's the correct answer. But I got 416 as an answer. Oh, so far we're doing everything correctly, so that's good. Yeah, so I don't know why they did that. Like, I just divided by 3,600. Like, if I didn't do that, it would be the 1.5 million number down here. That's what we have for seconds. And divide by 60, I get 417. So this 41.7, I think they just put the decimal in the wrong spot. Just gonna move on. Unless, put in the comments if you know where I made the mistake. I do make mistakes all the time. It's always good to know. The number of Xeon particles that would have to be discharged in order to increase the speed by 1 meter per second. Okay, so you keep on changing numbers around here a bunch. Would have to be how many atoms? Okay. So, so they want us to say that if the impulse of one is one direction, then the impulse in the other direction has to be the same, right? That's just Newton's laws. So if I use this information that I have here, let me just erase all this ink here, that the momentum of the the satellite is going to be equal, the impulse, is going to be equal to, at least the absolute value, is going to be equal to the impulse going the other direction too, because in Newton's third law. So if Xeon particles apply a force on the satellite pushes back for that same amount of time. So this is just for 1 second. So we got a force actually. So we got a force times time for the satellite side. All right, I probably could just do this a little bit better here. So rather than write it that way, I can say the impulse of one is equal to the impulse of the other, and just pick appropriate formulas for these. So I'm going to go force times time for the satellite side. So it's 1 meter per second oh yeah, sorry, it won't be force times time. It'd be mass times change in velocity. So it's going to be 1 meter per second for the 2,500. So this side over here is 2,500 Newton seconds, right? That's 1 meter per second, and that's going to be equal to the mass times the change in velocity on the other side. And you can see here, there's my velocity, exit speed. Remember, the initial speed was negligible. So I'd have like final minus initial, but my initial was close enough to being 0, so we can ignore that. So we can find the mass by dividing this final speed over to the other side. So I've got this 2,500. I'm going to divide by the 15,000 from the question. So we get a mass of 0.16666 kilograms. Okay, then I have this number here. How many fit into that, right? So how many of those fit in? So what we're going to do is just divide these two numbers. Okay. We're going to have lots of Xeon particles here. You can see from the answers that we're going to have lots. So we're going to divide by that smaller number, and we get that last one, 7.6 times 10 to the 23. There you go. Okay, so we got this negatively charged particle here, hanging off to the side. We're going to use this for questions 10, 11, 12, and numeric response number 2. Let me see what we have for it. Cool. And all right. All right, so one way, so what they want to do is they want to charge this. They want to charge this graphite with a net and negative charge, and they want to touch it. So touch its contact, conduction, or conduction. So that's going to be the last one, or it's B here. But I also want to charge it with negatively, so it's got to be D. All right, that's a pretty simple concept, so I'm not going to go too much depth about that one. The charge is what? So what do we have here? experiences electric force. Okay, so yeah. So they want to know that charge. So what we're going to do is we're going to look at this picture here. We got a few different numbers. I think this is all we need here. Okay. So to find the charge, we have an electric force. So this is my Fe. And we have to remember that Fe, if I were just rearrange the formula that's behind my head here, right there, right, is going to be equal to E times Q. But what is E? Well, to find E, I'm going to have to rearrange or do this other calculation that's behind my head here too. Delta V divided by D here. So delta V divided by delta D times that Q. So that's my E there, right? And I got all this information here. We got 310 volts. We got a distance here of 20 centimeters. So I'm just going to change it to meters. And we're looking for Q. I should have rearranged it before I did this, but that's fine. Now I can rearrange it for Q. So I'm going to times it by 0.2 divided by 320, and I'm going to get my charge. Times by 0.2 divided by 310, sorry. And I get a Q of 5.419 times 10 to the negative 10 coulombs. Okay. Sorry about the way I wrote that. So what do they want? 2 sig digs and 2 decimal or 2 digit exponent. So 5410. 5410. There you go. Okay, so what would the free body diagram look like here? This is a pretty easy one. The only reason it's getting pushed off to the side is because the electric force is pulling it that way. So the electric force must be going to the right to pull it to the right. So it doesn't make sense you to go B or D. It's going to be one of those two. And most of the time we assume that gravity is negligible. But when it comes to these larger parts, it's always there. Like even in a free body diagram, you'd always try to draw it anyway. And if you try to draw for this one, the only reason it stays there, because if I draw C, it's going to like fly off in that direction there, right? The only reason it's stationary is because you have this balancing force, this gravity. So it's got to be A. Right? There's definitely enough mass there to cause that. The charged plates are now removed. The positive plates replaced with the north pole of a strong magnet and a negatively charged. Okay. The system is allowed to reach equilibrium. As a result, the magnetic field, the negatively charged particle will. Why would it swing back and forth? It would move down, like it would be removed, and then the system allows to reach equilibrium. So it would swing down. As it swings down, it would produce a force that would kind of deflect it in a perpendicular direction and would kind of swing. And eventually, I think it would just kind of settle down at the bottom and just hang midway between the poles. Because it's not going to be attracted unless it's like moving all the time. It might move in a kind of a circular motion, right? It says it's going to reach equilibrium, so it's probably going to, I assume it's going to stop, but it might move in this kind of circular motion. Gotta think about how that's going to work. No, it won't, because it's moving in the same direction as. Yeah, so it's just going to hang midway. Okay, never mind. Yeah, I just want to see if that's right. Question 12 here. Submit test. Is it? Yeah, that's right. Okay, so far that's right. Return the test. Okay, not too bad. Yeah, because I'm going to zoom in. I'm going to talk about why that's the case. You might think, oh, it's deflected because this moving negative charge is going to produce an electric field. But if I use my hand rules, okay, for some reason I can't grab that. And zoom out here. Okay, so there's moving, I could just do it here. Okay, let's go back there. So they replaced the positive with the north pole or south pole, it doesn't really matter. All right, so say this gets replaced with a north, this gets replaced with a south. So we got this magnetic field going this direction now. The particle, the negative charge particle, is going to move in this direction. That's my velocity there. So if I try to use my hand rule, it's a negative charge, so I use my left hand, and I try to orient my hand in a way to get my thumb and my field, my thumb and my field in the same direction. I can't, because I had to move my thumb this way so they'd be parallel. So there wouldn't be any force. It would just sit down because of gravity. That's it. There might be a little bit of force because of downwards trajectory, and there might be a little bit of force outwards, and it might cause a little spiral, but eventually it would have to stop. So it's got to hang midway. All right. Two metal spheres are sitting on an insulated stand, giving a static charge, blah, blah, blah. They're faced, what's point P halfway between them? Okay, so we're going to have to draw a little picture here and do a little math. So the key is that it's halfway, right? So since it's halfway, here's one charge particle. Let me move my face out of the way. So this I'm going to give the -4 times 10 to the -6 coulombs. And then over here, I'm going to give this the positive charge, the 2 times 10 to the -6 coulombs. And we look at this point P here. What's the electric field at that point? That's halfway. The spheres are then placed 0.5 meters apart. Yep. So this distance is half of the 0.5, so 0.25 meters. And this distance is also 0.25 meters. Okay, so based on our charges here, this -1, because it's negative, it's going to be attracting positive things. So it would produce an electric field going to the left, going towards it. And then the positive one here is also going to produce an electric field going to the left. It's going to be about half the size because it's half the charge, same distance. But it's going outwards because it's positive. So they're both going in the same direction. So when I do the math, I got to make sure to add those two magnitudes together. So this side here, I'm just going to go KQ over R squared, and this side I'm going to do the same thing, KQ over R squared. Okay, so I'm just going to do the calculations separately here. Remember K being 8.99 times 10 to the 9 times the 4 -6 times 10 to the -6 divided by the distance squared. We get this nice big number here, so I get 575,360 newtons per coulomb. And then this one, so what I'm getting here is just the magnitudes, right? The directions for my picture, they're both going to the left, right? So don't get confused. Don't put negatives into this formula because it just really confuses people. Make sure you square those distances, and you notice that this number, because it's half the charge, but everything else stays the same, it's just half the charge, it's going to be half of the electric field. But they're both going in the same direction, so you're going to add them together, and you get 800,000. Hey, that's A there. Okay, let's go back here. So A. Okay. All electric camera flashes, there are capacitors, which is a device that allows a large quantity of charge to be charged, and then it kind of disperses. And then you got this formula for capacitance here. The energy stored in the capacitor is equal 1/2 FV squared. Okay, so here they just want us to rearrange this formula to get F by itself and then put all the appropriate units in here. V is a potential difference, so that's the volts. F is the capacitance, and E is going to be energy, which is in joules. So if I rearrange this formula for F, I'm going to have joules on the top. I'm going to divide by volts. Oh, but that's not in here, so we're going to have to do it a little bit differently because a volt is a very specific type of unit. You see they wanted to be in coulombs as well. So I'm just going to snip this out. That would have been way too easy. Let's see what we can get here. Okay, so here we have joules, and then we're looking for whatever F happens to be, a farad or something, yeah. I could put that there. And then we have a volt squared. Okay, so remember a volt is, if I have a couple of formulas for it, where did I put it? Right here. A volt is equal to electric field times distance, or there's another formula up there. It's equal to energy divided by coulombs. Okay, so this one's being squared, so it's going to be volt is equal to a joule per coulomb. A joule per coulomb, that's going to be squared. Okay, so that's going to be joule squared per coulomb squared. I'm just going to cancel one of these out. Actually, I'm just going to rearrange it first. We've got times the c squared up, divide the joule down. So we get c squared in the numerator. Got to fly my face there. And I'm going to divide this by a joule. That's what I get for it. C squared over j. Sweet. There you go. Anything else here? Good. Electron is initially at rest near a negatively charged plate. At the instant illustrated by below, the electron has 50 electron volts of kinetic energy. At any point along the path, the sum of the kinetic energy and the potential energy will be what? And they wanted electron volts. So what would the sum be? So we know this has this much electrical kinetic energy at this point, right? We don't know how much potential it has at that point. So we could just find out how much potential it would have by using this formula, right? So it's an electron. We got this. So let me just go here. Oh, it's going to be 215 is my answer. Let me just write that down, and I'll explain how I got that. Okay, so we're going to snip this. I'm just going to take that part right there. Now, what's happening is we got an electron, so we know the charge of an electron is 1.6 times 10 to the negative 19 coulombs, right? I'm ignoring this 50 electron volts. That's kind of useless information at this point because we're looking for the sum of the two, so we're kind of looking for the net. So I'm just going to imagine that it's initially at rest down here, right? So I'm going to be using this formula to find out what the potential change in energy could be, which gives me the initial amount of energy, because if I say my final or my initial is equal to 0, then I can just rearrange this for my final energy. And based on conservation of energy, that final energy is like its net energy. It's mechanical energy at that point. All right, so I got this delta V times Q. And then what I'm going to do is I'm going to times it by 1.6 times 10 to the negative 19. And that's going to get me joules. All right, I'm not going to do that math. But what I'm going to do is I'm going to divide it by 1.6 times 10 to the negative 19 joules per electron volt, because I want to change the electron volts. But you notice what's going to happen is that these two numbers are going to cross off. The units are not going to cross off. They're going to do their thing. And I'm going to end up with 215 electron volts of energy. There you go. That's where that number comes from. All right, so what do we have here? Electron enters a parallel plate system here. The path taken by this will resemble the path taken by an alpha particle. No, because, okay, so what happens is it's going to be a rock thrown horizontally off a cliff. And the reason behind that is because it's going to be attracted downwards. The force is always going to be remaining the same, like gravity always acts down. So the electric force will always act down, so it creates a parabolic motion. An alpha particle in a magnetic field is going to, because of the hand rule, always changes direction. The force always changes direction, creates circular motion. Hammer, a circular motion. Oil drop released in an opposite charged plate. That's just going to accelerate straight up and down. It's not going to be parabolic. So it's going to have to be A. because B and C are circular and D not. When molecules in biological samples alternate ions, let's go see what kind of ions we're creating here. Well, we can't add or remove protons. It's all about electrons. But what kind of ions are they? Positive or negative ions? Gotta read through this here. Ions are placed on one end. I can kind of guess what kind they are because they're being attracted down towards the positive plate. They're going to be negative ions, so that means electrons were added here. Okay, because they're being attracted downwards, so they're negative. I don't know if it specifies in there, but I just saw from the picture. They're negatively charged ions. Okay. Remember, you can't add or remove protons. It's all about electrons. As the ion moves towards the positive plate, the magnitude of electric force remains constant. It's constant as the force. Constant. Increases, decreases, increases. Yep, it's just going to be constant, right? Because remember, the electrical field between the plates remains constant. Through a bunch of calculus and a bunch of other things, right? So this formula that's right above my head here, that only works for like 2 charges, right? But we got lots and lots of charges on both sides. As you get closer to one, you're getting further from the other. They kind of balance each other out. So the field stays constant within. It's very complex math, but it works. What is the electric field, though? That's what they're asking. So we got the voltage, we got the distance. That seems pretty easy. We just take the voltage divided by the distance. So 200 divided by 0.1, I'm not going to do too much there. It's 2,000 volts. And they want 2003 then. 2003. I'm not even going to bother writing that down. Just going to skip on. Okay, during the experiment, so this might be a bit more harder. During the experiment, the DNA moves from 0.3 through the gel. What do we have to do here? Then the work done by the electrostatic force to move the ion is what? So we're looking for that change in energy here. I don't know what happened here. That's probably supposed to be 10 to the power of 2 rather than being 102 like that. Right. So how are we going to determine what the work done is? So that's my delta E. So we have to determine the voltage. So this is a good question because this 200 volts that they have here is for the whole distance, right? But we're only moving 3 centimeters, not 10 centimeters. So let me just snip this and I'll show you what I mean again. And then we can figure out that work done. Okay, so this number, this 200 volts, corresponds to the 10 centimeters, right? So if I change this is 10 centimeters here. Right. So we're gonna have to do like a proportional reasoning here. So if 10 centimeters is 200 volts, then how much is 3 centimeters, right? Because the volts is how much energy changed per coulomb. If I don't move the whole distance, I'm not gonna change the whole energy. So I gotta do a little proportional reasoning. 3 times 200 divided by 10. This is only 60 volts. So the change here, the delta V for the 3 centimeters is only 60 volts, is not the whole 200 volts. Then, I think it said it was 2, right? Yeah, and then what I'm going to do here is I'm going to take that, put it into my delta V times Q formula. Q, 2 times that 1.6 number there. 3.2 times 10 to the negative 19. So we got 1.9 times 10 to the negative 17. Not good. And then I'm going to divide this by 1.6 times 10 to the negative 19. To get into electron volts, it's 120 electron volts. So that would be A. All right, the reason I knew I had to change it because the number didn't work out. All right, so the answer is going to be A. So we have to do that first. Let me just write some stuff down here so you see what I'm talking about. 60 volts times the 3.2 times 10 to the negative 19. And that's going to get me like this 1.9 number. 1.92 times 10 to the negative 17. joules. That's not anywhere on there, so what I had to do is I had to divide by this 1.6 times 10 to the negative 19 joules per electron volt number, and that's going to change it into the 120 that we had. Sweet. All right, so this is a very common question. So gravitational fields are caused by mass. So anything with mass has a gravitational field, right? So this is like the electron is producing. So we always say the electron gravitational force on Earth is relatively small, and we kind of ignore it, but it is producing its own field because it has its own mass, it's just really, really weak. So mass creates that. Constant electric field, that's going to be charge. And to create a magnetic field, you can see here it wants two things. Remember, one of Maxwell's predictions says that a moving charge produces a magnetic field. So we get a charge, and it has to have some speed here. So I'm going to go 2113 there. Electromagnetic waves are produced by, oh, I just said it, didn't I? An accelerating charge. There we go. Accelerate charge. The previous one I said was moving charge. Maxwell's prediction says you have to accelerate the charge to produce EMR. My bad. All right, several methods used to estimate the speed of light. Eclipses of Jupiter, uncovering, recovering light. That's like super inaccurate. So that's the least accurate thing we're probably going to do. Observing interference patterns produced by a single source of light that travels slightly different but precisely measured. Obviously, that's given the word precisely measured distances and stuff. So I'm going to have to go 1 and 3 there. So 3 is probably the most accurate because of precisely difference. Interference patterns, single source light. It's just, there's so much precision there. You don't even have to know what that is. I think it's the Michelson experiment. I think it is. So, okay. Oh, here's the Michelson experiment. What's the minimum frequency? So remember on this, we're going to have to remember Michelson's equation, right? So it's an 8-sided mirror. We've got some distance here. Go. So remember Michelson's equation is, move this out of the way here, is C, this is the formula that's not on your formula sheet, 2DNF. It was developed in class, right? So you don't have to know how it was developed anymore. You just have to know what it is. The 2 just stands for there and back. So if they give you the total distance already, don't put the 2 in the equation. But since they only give me the one-way distance, the 35 kilometers, it's going to go back. Remember, 35 kilometers is 35,000 meters. So make sure you times that by 2. Okay, so we're looking for F here. So we C is equal to 2 over dN. And N being the number of meters, we've got 8, D being the 70,000. And if they don't tell you what the speed of light is in the question, just assume it's the 3 times 10 to the 8. Where's that 8? So I get 536. So that's going to be A. Oh, one of these. These ones always trick people up. Okay, so when white light enters through, it kind of refracts. You can see here the blue light is refracting more because it slows down more because it has a higher index of refraction inside this glass bead here. Okay. Which of the following statements valid predicts? So index of refraction is greater for red light. No, so blue light, shorter wavelengths refract more. The reason they refract more is because they slow down more. If they slow down more, let me just go through the formula here. This is one formula which is also not on our formula sheet. All right. So the formula which I'm talking about is this one here. All right. V is equal to C over N. N is, I can rearrange this for C over V, right? That's how you calculate the index of refraction. So if this speed goes down, the index of refraction has to go up, right? So blue, which is bending more because of the bigger speed difference, is going to have a higher index of refraction. So blue, higher index of refraction. So it can't be A because it says your red has a higher index of refraction. It's less than violet light because refracts less. That makes more sense. I kind of like that answer so far. Let's read through the rest ones. Index of refraction is greater because violet refracts more. What's the difference between those two things? Red is less because it refracts less, is greater because violet refracts more. Okay, I don't like D or A. What's the difference between B and C? Okay, let's double check this here. The index of refraction of red light is less than violet because red refracts less. I kind of like C as a better explanation. It's greater more because it refracts more. There's a bigger angle of refraction. What did they say it was? Oh, what happened to 18? I have to go back there. So, I don't like that. They probably want it to be B. Yeah, weird. Return to test. I gotta read through this again. The index of refraction of red light in flint grass is less than violet because red refracts less. The index of refraction in flint grass is greater than red because violet refracts more. They're essentially saying the same thing. Okay, and plus also, I have to go back here. What's multiple choice number 18? What did I mess up on that one? What do they want this to be? During the I got 120. Let me double check here. So it only moved 3. What's the work done to move the ions? I hope doubly charged, so 2e makes sense. Get divided by. I want to know if they messed. If I put here C for some reason, nope, still. It's not in joules. I moved it away from joules. It's got to be A. I'm gonna call BS. Do we even have a right answer here? No. What do they want for an answer? Return to this. D. They want D as the answer. No, that's not even close. It's got to be A. Never mind. I'm just going to quit there. Okay, it's A. Okay, let's go back here. Where are we? This one here, I don't like these questions because these are saying the same thing unless they're not. Index of refraction is less because it refracts less. The index of refraction is greater because it refracts more. Which is a valid reason for the index of refraction of red. Actually, I like C more because that's the way I think about it. Let's say put B. Okay, whatever. Okay, so I would have went C on that last one. On a particular day, the index of refraction is this. What's the critical angle? Okay, so remember when you're doing critical angles, we have to make one of the angles equal to 90 degrees, right? So we got light coming in, or EMR, hitting the atmosphere at a specific angle that we're trying to find, this critical angle, and then it's going to refract back, or reflect backwards, sorry, because the angle of refraction is 90 degrees, right? So then it creates total internal reflection. So let's just call this down here air. Atmosphere is 1.8. So that's 1.8 up here. 1.81. Missed it. Yeah, 1.81. Let's call that N2. Right? N1 is 1.00. So we're looking for our critical angle. Oh, we got to go the other way because this would be space then. I would have messed that up, but it would have kind of corrected itself. So down here, and then it's going to speed up on the way out. So We got 1.8 down here, 1.00 here, and then sine 90 degrees. If I had them the wrong way and I tried to do the math, it would just yell at me. I would just flip them over anyway. So even if I got it wrong, I would have got it right. So 33.5. Yeah, 33.5. Now what you're going to do, you're going to cross multiply divide, right? And then you're going to go the sine inverse of, because sine 90 is 1, but you can times it up if you want. And if these were upside down, the math wouldn't work. So you got to make sure that's the right way. So 1 over 1.8. No, 32.5, yep. Okay, so concave mirror here. We're trying to figure out what the object distance is. You got this nice little picture here, but the picture there is kind of help you kind of label off certain things, like what do all these actual numbers mean here? So the numbers they give us, this 2.4 from the focal point, is not the full distance of the object, right? So that's only from here to here. And then from the focal point all the way over to here is 4.3. So the object distance is actually 6.7. Right? Because that has to be measured all the way to the vertex. So that's going to be key. The focal distance, because it's a concave mirror, is going to be positive 4.3 centimeters. And we're just looking for the image distance, right? Yeah. So what does that end up being? So we've got 1 over f is equal to 1 over do plus 1 over di. And then we're going to just rearrange this. So we got 1 over 4.3, 1 over 6.7, plus 1 over di. We can solve that. So I'm not going to go through too much rearranging here. We're just going to minus over this 1 over number first. Oh, 6.7. And then do the reciprocal. Oh, yeah, that's not going to work too well. Okay, I got to redo my math, sorry. There we go. Get 12. That's a D. Cool. I wonder if I can do like a picture. Should we somewhere about here? More than a 6. So it's got to be 12. Yep. Not a very good picture. Okay, so 12. Let's put that there. Okay, the energy emitted by one photon. Oh, I have to go over here. Do this equation. Is what? So we got some information over here. So the uses a monochromatic laser of 630. Okay, so we're just going to use the HC over lambda formula here. I'm not going to show too much here. I'm just going to do it in my calculator. Make sure you use the 6.63 because I want my answer to be in joule. 6.63 times negative 35. And make sure to change your number into regular meters. Man, it should just be a pretty simple calculation. It's going to be the negative 19 answer right there at the bottom, 3.14. Negative 19. Sweet. Okay, procedure 1, the wavelength of the laser crystal is blank. So it's going to go in the crystal. It's going to decrease. So I can use Snell's law to figure what that is. Really just, actually, I probably figured this out. Is it going to decrease or increase? It's going to slow down. I think that means the wavelength is going to go down. So I could just do some of the math here using Snell's law. I think I have an answer already, but I just double check. Okay, so we are going to just plug in some Snell. So N, oh, my face here. Come on, move my face over there. So N2 over N1, lambda 1 over lambda 2. So we're trying to find N2. That's in this or lambda, we're trying to find lambda 2. So we're trying to find that. We have 1.53 here. I'm assuming this number is in the air. I think it says somewhere in there it is. It doesn't say that, but let's say assume it is. Cross multiply, divide. Yeah, so cross multiply, divide. So I'm just going to divide by 1.53. So we have 412, 414. So it's got to be A or B. And then when compared, the speed of the laser in air, the speed in the crystal is going to be less. Yeah, that's the index fraction. It's got to be less. Why would it be more? It can't be. Okay, so A. Procedure 2, the angle is what? So using lambda, and what are we trying to find? The light that passes through the fraction. To which one? To the first of bright spot. So lambda is equal to nd, or n, not n. So lambda is equal to d sine theta over n. That's what it is. Okay, so we got lambda. I'm just going to rearrange it in my head. So times by 1, divide it by the d there, and take the sine inverse. Oh, sine inverse of my answer. So we got 18 degrees, 18.5. Is that what they want? Yep. Let's see how I'm doing so far. Yay, it's just 18. Garbage question. Okay. In order to produce an electrical current, you must have the student directs the laser, no current is produced. So they want a wavelength that's shorter. The shorter the wavelength, the more energy. All right, because right now it's not doing anything, so we need more energy. So we need a shorter wavelength, or that has a smaller work function. Yeah, makes sense. Work function is the energy required to get the electron out. So if I have less energy required, like less energetic photons, we're going to work just fine there. Which is the fine range to increasing, so lower to higher. No, not the first one. Yeah, the second one sounds good. Gamma's too high, microwaves, ultraviolet, visible. Those are kind of all over the place here. Microwaves and infrared would be on the same side. So yeah, it's going to be this one here. Remember, it goes radio, infrared, visible, ultraviolet, X-ray, gamma. All right, well, microwaves in there too, but back at radio, microwave, infrared. So they didn't put visible in here, but visible would be between infrared and ultraviolet there. Good. All right. So photocathode has a threshold frequency. It's illuminated. What's the maximum kinetic energy? So remember, this formula is not on your formula sheet, so you're going to have to remember this one. All right, it's just conservation of energy. So the energy of the photon is equal to work plus the kinetic energy. So the energy of the photon, HF, because they give us the frequency, work functions HF naught, my frequency there, my threshold frequency. And we're just going to rearrange it. So I just want to, you want it in joules here, so we're going to use the 6.63 number. I should put negative, there we go, times my frequency of my light. I'm just going to do the first side first. I'm going to do the left side. So over here I get 5.4366 times 10 to the negative 19. So I'll probably cross off C. Doesn't make any sense. It would be that one. And then 6.63 times the threshold frequency. So I only required 3.6, or 3.7, sorry, times 10 to the negative 19 joules. So I'm just going to minus this over to the other side here. 5.4366 e to the negative 19 minus my answer. So I'm going to get A there. There we go. A. Done. Ooh, which one explains the Compton effect? The Compton effect explains the particle nature of light. the ejection of electrons, that's the photoelectric effect. This one requires, the explanation requires that there's particle nature of light. Like the packets of energy, even though they're just pure energy with no mass, they have momentum. Okay. One immediate result of the cathode ray discovery was that electrons exist. No. No, that would be the gold foil. The atom mostly end up empty space. That's gold foil. So it'd be D. Because that plum pudding model, they discovered the electrons within the atom. All right, the analysis of the Rutherford alpha particle scattering led to the model in which the 10 to the negative, the diameter, and the nucleus 10 to the negative 15. Okay, so the atom is the larger part. The nucleus is this tiny little thing in the middle. So maybe that's the alpha particle experiment, mostly empty space. So the atom is the bigger number, so negative 10. So atom, nucleus, and the majority of the mass is inside. So atom, nucleus, mass. Right? The charge is evenly distributed, right? You got all the positive in the middle, you got all the negative on the outside. It's like equal, right? So not going to be most of the charge inside, it's going to be most of the mass. Okay. So we want to ionize an atom. Do we want to ionize? If it exists in the 1.6 level, what's the minute frequency ionizes? So just to get to the top there. So to get to the top, to get to 0, I just require 1.6 electron volts. So I'm just going to use the HF formula here. I'm going to use the electron volt version of H to solve this. And it's going to be the 3.9 at the top there. That's a pretty fast little question. All right. For which of the following explanations does diffraction of high speed provide high speed electrons? De Broglie's explanation of wave nature of matter. I kind of like that one because the electrons are mass. Why are they diffracting? Why are they interfering with each other? It doesn't make any sense. So it's got to be that the idea that this matter behaves as if it's waves, and waves behave as if it has matter, right? So de Broglie. Which of the following best describes the decay of cobalt? So what kind of decay is it? Over here, is it beta positive or beta negative? Cobalt radiation, half-life decays, emitting beta negative particles. So I don't know why you'd pick C or D because it's a beta positive. Then you just have to make sure it actually works. Actually, you just look at the one that gives us the beta negative is a regular matter. It's got to release the antimatter, so it's got to be B. Because they both have the balancing here, but it's got to be that antimatter particle there. Beta negative, anti-neutrino. Beta positive, a regular neutrino. So C would be right if it was beta positive. What remains after 15 years? Okay, so remember our formula that we don't have on our formula sheet completely, right? We have most of it. Was it this, what's it, half-life? I can't read it over there. 5.2 years, okay. So the formula that we have has an N, it has a lot of N's in it, it's for half-life here. So the formula says N is equal to N naught 1/2 to the power of N. Remember, N is just the number of half-lives, and to calculate that N, that's going to be T over P, all right? Time 15.6 divided by the 5.2, that's going to be 3 half-lives, all right? So this is going to be the 15.6 divided by the 5.2, and you get 3 half-lives. Oops, half-lives. Okay, so now we have 3. So there's a couple of different ways to do this. You could plug it into our formula sheet or into the formula here. We want to determine percentage, so let's just say we start off with 100%, and we raise this to the power of 3. So it's just 100 divided by 8 essentially, but if you want to do it the other way, you can. So you get 12.5%. Well, 3-digit answers to 12.5. There you go. 12.5. All right, energy released in this nuclear fission reaction is because the mass is less. Mass of what? Yeah, I've lost mass. Where'd the mass go? Well, it must have went to energy, right? So energy in nuclear reactions are always because of a mass defect, not because of this other stuff here. Always a mass defect. Then you can find that out if you need to. In this case, do we have to determine that? No, we don't. But this, right. At a particular instant, the electrostatic force, the deuterium, exerts on the tritium, 23 newtons. The distance between the center of the atoms, ions, is what? Oh, so what do we know about these things? Do we know the charges? These are just ions, right? Or the atoms? Oh yeah, they're ions. Okay, so they're both positive 1. If they lose, because they only have 1 electron each, if they were atoms. So they're both positive 1, even though this has 3 nucleons. They both have 1 neutron, or 1 proton, so they must add 1 electron. So if I lost that electron, they both become positive 1. So when I do my calculation here, to figure out this, we have this electrostatic force is 23 newtons. And then I'm just going to go KQQ over R squared. We're looking for R. We'll just rearrange for R squared first. These charges are both the same. So they're going to be 1 elementary charge because they're 1 proton each. So they're going to have this. You could just square this number if you wanted to. You can just write it out twice. It's up to you. We're divided by 23. K is that 8.99 number again. And then I'm just going to type this in my calculator really quickly. Divided by 23. Oh, and then what I have to do here is I got to make sure to take that square root. Right, so I got to get rid of this part. So I take that square root of that whole number. Just kind of cut right through there. So I want the 2 sig to get answer, so it's 3, 2, and then 15, a negative 15 exponent there. So 3, 2, 1, 5. It's kind of a weird question. Kind of in the middle of nowhere. What's the direction? So this is out of the screen. So we're going to use our hand rule. So we got this positively charged ion, right? So we got this ion flying in, positive charge. I'm going to use my right hand. We got the field going out of the page there. So if I kind of orient myself there, you can see my force is towards the bottom of the page. All right? Yep, towards the bottom of the page. Cool. Not bad. We'll just cruise these last couple questions here. Neutron producing this escapes magnetic because, or the neutral particles are not deflected by magnetic fields because, remember, magnetic fields are produced by moving charges. If they don't have a charge, they're not going to produce a magnetic field. And they're not going to interact with magnetic fields. All right? Lots of good answers. No, I think A is a good answer for that one. I just want to see if that's what they wanted. Yeah, that's what they wanted. Okay. Oh, we only have 3 more questions. 4 more questions here. We're doing pretty good. All right. In this particular instance, it's traveling at 5.2 million meters per second, hits a lithium blanket, stops. What's the impulse? And the collision is classified mostly inelastic because it comes to a stop. All right. So you have all this kinetic energy, you lose it all. So it's obviously inelastic, so it's going to be one of these two. And what are you trying to find here? The impulse. So these units are a bit weird because this is energy. So I want to say it's B just based on units alone, but let's just double check. So to find impulse, change of velocity. So it's going to be negative because I got final being 0. And then we got this, I'm going to times it by its mass. The mass of a neutron. So I find a neutron, it's just going to be on our formula sheet, right? 1.67 times 10 to the negative 27. Yeah, it's going to be B. I don't know why I did ask for energy. Why would you put energy? This is impulse. Mass times change in velocity. Okay. Which is most likely the neutron So it comes together. You can probably read through here exactly what's happening down here. Do they fuse together? One way to harness the energy of this, one of the problems with this requires overcoming a particular reactor. However, neutrons escape. These neutrons are captured by a lithium blanket. So they're just going to collide with the lithium and get captured. So just have to figure which one makes sense. Okay, so lithium. Well, lithium, the most common form of lithium, if I look at here, is lithium 7. It says 6.94 on the formula sheet, right? So 6.94, if I round that, the most common is 7. So it's most likely going to be, this is most likely. So it's going to be A or C, and then I just have to make sure all the math works out. 8 over 3, or is it? Oh yeah, so this one's not true because the bottom can't be 1. 1 is the charge. Neutrons are neutral, so it's got to be A as my most likely example here. Yep. In order to study subatomic particles, high energy because the strength of the strong nuclear force. The strong nuclear force is pretty hard to overcome. It's pretty strong, right? The strength, because you want to try to pull these things apart, and you have to get past them or break them so they break apart. Electrostatic forces. Oh, maybe which one is it? Electrostatic force. You want to get them pretty close to each other, so you want to be able to get them to touch, essentially, so you get past the electrostatic. I think it's electrostatic force. It's going to strong nuclear force. No, let's go electrostatic force in this one. I like that answer. I'm going to pick that one. Oh, it's not that one. It's a strong nuclear force. They want it to be the strong nuclear force. Blah, blah, blah. I do like that I had to overcome the strength of the electrostatic force too, because you have to get pretty close to each other. The closer you are, the bigger the force. But my first instinct was a strong nuclear force. Now, kind of like that. And my last question here, which of the following describes beta positive decay? So obviously it's not A and C. So you got the right particles for those two. Now I just have to make sure I have beta positive. So I have to look at the charges of both these sides here, right? So I've already crossed off the beta negative ones because I'm looking for beta positive. Now which of these works? So if I look at the charges, an up is a 2/3. Then a down is a negative 1/3 and another negative 1/3. So this is for this one here, all right? So up, down, down, that's going to be 0. And then on the other side, I'm going to want to make sure it ends up being 0 as well because conservation of charge. And I can already see this is not going to work because 2/3 plus 2/3 minus 1/3 is 1 plus the 1 already, that's 2. That doesn't work. So can't be that one. Cross that one off. All right, let's double check this bottom one here. So this is going to be 2/3 plus 2/3 minus 1/3. So that's 1. So the other side's going to have to be 1 as well. And then we got an up minus 1/3 minus 1/3. That's 0 plus 1. So that balances out. So it's got to be D. Yay, and that question C. That's really annoying me. I'm just going to stick with that answer for question C. And there you go. All right. I will see you later. Bye.